Hi everyone, welcome to Easy Examples, Learn Optimization Visually. Today we study Banner's decomposition through a small example. Banner's decomposition is a method usually introduced in advanced operations research. In most teaching materials, it is introduced by the general mathematical form, which might be hard for many people. So I designed this small example in this video. So what is Banner's decomposition? Banner's decomposition is a method to solve large-scale mixed integer program. The general idea of Banner's decomposition can be summarized as follows. Suppose that there is a big optimization problem with many decision variables. We call this big problem the original problem. The general idea of Banner's decomposition is to divide this big problem into two small problems, the master problem and the subproblem. Each of them only includes parts of the decision variables. Then, based on synchronizing mechanism, the two small problems are synchronized so that the solutions they find are consistent with the original problems. Here is the example question I like to use to explain Banner's decomposition. Suppose that there is a person, Mike. He has $1,000 to make a finance plan. He has two options: to simply put the money into the saving account or to buy mutual fund. For a saving account, interest rate is 4.5% for a year, and this account doesn't accept fractional amount, so it has to be integer. For the mutual fund, there are 10 available options, F1, F2 to F10, which have the rate of return at 1%, 2% to 10% respectively. For each fund, Mike can only purchase $100 at maximum. And the question is, what is the optimal finance plan? The answer is obvious. He needs to buy $100 of F5, F6 to F10. That is the maximum amount because these funds have higher interest rate, the rate of return, than the saving account, and he should put the rest money into the saving account. In this video, I'm gonna use the Banner's decomposition to solve this optimization problem and find the same answer. Now let's look at the mathematical model for our example question. Here are the decision variables. The y here is the amount to put to the saving account, and the x are the purchase of mutual fund. X1 to X10 are the purchase of fund 1, F1 to F10. This is the optimization model, and it is very straightforward. The objective function is to maximize the return from the investment and the savings, and the coefficients are the rate of return for each fund and the saving account. The first constraint that the total amount used to buy mutual fund and to put into saving account should not exceed 1,000, which is the Mike's budget. And the following constraints that for each fund, the maximum purchase should not exceed 100. This constraint that the amount to put into saving account has to be integer, and the last constraint constrains the decision variables to be non-negative. In order to introduce Banner's decomposition clearly, we first need to write our model in standard form. This is the standard form. It's written in vectors and matrices. The vectors of x and y are the vectors of variables, and in the objective function, the vector c includes all the coefficients of x and f is the coefficient vector of y. The capital Y is a set that defines all constraints that includes only y. For the constraint that includes both variables x and y, the capital A is coefficient matrix of x and the capital B is the coefficient matrix of y. The lowercase b is the vector of the right-hand side constant of the constraint that includes both variable x and y. This is the actual value for each vector and the matrix for our example question. These are the detailed steps of Benner's decomposition. Now I will use our example to explain each step. At the beginning of Benner's decomposition, we need to initialize the solution of master problem. The y star here means the solution of y in the master problem. This is the definition of master problem. In the objective function, it only includes a newly introduced variable z, and in the constraint, y only need to satisfy the y constraint in the original problem to be feasible. For our example question, y only need to be non-negative integer, so we initialize y as 1500. For the upper bound and lower bound of Benner's decomposition, we initialize them as positive infinity and negative infinity. After the initialization, we come to the body of iteration. Here, the epsilon is the gap limit we set for Benner's decomposition. When the gap between upper bound and lower bound is lower than this gap limit, then the iteration is terminated. The smaller limit means the more accurate. For our example, we set this gap limit to be 0.1. The first step in each iteration is solving the dual of the subproblem, and the optimal dual solution is denoted as U star. So what is the definition of the subproblem? Recall this form of the original problem. When y equals to y star, this y term in the objective function is not necessary, so we can remove it. This y only constraint is also not necessary, we can remove it. This y term is constant, so we can move it to the right hand side of this inequation. After all the transformation, we have a new form, and this is the form of the subproblem. When we have the primal form of the subproblem, we can easily derive the dual of the subproblem, and by solving this dual, we can have the U star. Now let's focus on our example. So far we have y star equals to 1500. Then based on this y star, we can formulate the dual of the subproblem. From the objective function of the dual of subproblem, we can see that if u1 equals to positive infinity and u2 to 11 equals to 0, then the objective value of the dual equals to negative infinity, which means that the dual of subproblem has unbounded solution, and the U star here is an extreme array. According to the theory of duality, if the optimal solution of the dual is unbounded, then the primal problem has no feasible solution. So in the following iterations, we add the cut to prevent this case to happen again. So after substitution, we get this cut for our example. It constrains that the amount to put into the saving account should be less than 1000. We solve the master problem with the cut we just added. Because so far the objective value z is not related to the variable y, so no matter which value you choose for y, the objective value z equals to positive infinity. So we randomly choose the y star to $1,000, and the objective value is positive infinity. The upper bound equals to z star, so far it is still positive infinity. Because the gap between the upper bound and lower bound is infinity, so we continue the iteration. Again, we formulate the dual of the subproblem based on the y star equals to 1,000, and we solve this program, and we solve the optimal dual solution. According to strong duality, the primal and the dual have the same objective value under the bounded optimal solution, and the objective value here represents the best profit that can be made from the investing, given the current y star. Then we can calculate the total profit from saving and investing, which is 1,045. And then we update the lower bound. The lower bound is actually the best profit we have calculated so far. When we have u star, we can write the objective value of the dual as a function of y. This is actually the best profit we can make from investing as a function of y. In order to integrate this information in the master problem, we add this new cut to the master problem. And after simple derivation, we can have this form of the cut. Now we solve the master problem with all the cuts. In the figure, the shaded area shows the feasible region of z and y. From the figure, we can see that the optimal solution should be y star equals to 0, and the objective value equals to 1100. Then we update the upper bound to the objective value. Because the gap between the upper bound and lower bound is higher than the gap limit, so the iteration continues. We solve the dual of the subproblem with y star equal to 0, and we solve the u star. With u star, we can solve the total profit that can be made from saving and investment equals to 1,055. Then we update the lower bound. Then we generate the new cut with the value of u star. Now we have 3 cuts in the master program. In the figure, the shaded area shows the feasible region of z and y with all 3 cuts added. And by solving this integer program, we can solve the optimal solution of y and the corresponding objective value, z star. When we have z star, we update the upper bound to z star. Because the gap of the current upper bound and lower bound is still higher than the preset limit, so the iteration continues. Again, we formulate the dual of the subproblem based on the current y star, and we solve this dual and get the optimal dual solution, u star. Based on y star and u star, we calculate the total profit that can be generated from the saving and the investing, and we update the lower bound. And again, a new cut is generated based on the current U star. With the new cut, we have 4 cuts in the master program. The figure shows the feasible region with the 4 cuts added, and after solving this master program, we have the optimal solution of y star equals to 500 and the corresponding objective value z star. We update the upper bound to z star. Compare the difference between the upper bound and the lower bound. We found that the gap is higher than the preset limit, so we continue the iteration. Again, we solve the due of the subproblem based on the current value of y star, and then we update the lower bound based on y star and u star. Then we generate the new cut based on u star and add it to the master problem. We solve the master problem. We solve the optimal solution of y and update the upper bound according to the objective value. Then we calculate the gap between the upper bound and the lower bound. We repeat this process until the gap between the upper bound and lower bound is lower than the gap limit, which is 0.1 in our example. We solve the due of the subproblem given y equals to 250, and we calculate the lower bound, and we generate the new cut. We solve the master problem with the new cut. We solve the optimal solution of y equals to 350. We update the upper bound and calculate the distance between the upper bound and lower bound. Again, we solve the due of the subproblem given the current value of y star, and we solve the lower bound and generate new cut. We solve the master problem with the new cut again, and we solve the optimal solution of y equals to 400. We solve the upper bound and calculate the distance between the upper bound and lower bound. We see that this gap is very close to the epsilon, 0.1, so we are very close to the end of the algorithm. We solve the due of the subproblem given y star equals to 400, and we update the lower bound. Here we see that lower bound equals to 1063, and it is equal to the upper bound, which means that we should stop our iteration here. At the end of the algorithm, the solution of y star is our final solution. In our example, it means in the optimal finance plan, we should put $400 to the saving account and use the rest money to buy the mutual fund. In order to get the optimal investment plan, we should solve the primal subproblem given y star equals to 400. And here is the result. It means we should not buy the fund F1 to F4 and should buy $100 of F5 to F10. And this result is consistent with our initial guess of the result. That is, buy $100 of F5 to F10 and put the rest money in saving account. So this is our demonstration of Bender's decomposition. And it might be very complicated when solving a simple problem, but it is very helpful when solving a complex, large-scale problem. So if you have some suggestions or questions, you can contact me from the email in the bottom. Thank you very much for watching. Have a good day.